Now for our last example, this example is once again taken from Skoog. This is number 17-32, page 439. So I highly suggest that you read the problem first before you continue on with this video. If you've read the problem, you will note that this particular problem, we tackled it very fleetingly in class. We didn't have a lot of time back then, so I'm trying to make up for it now by making this one last video about it. Or last couple of videos. I don't know how long this is gonna be. So once again, I've summarized the important information right over here. Also, I cannot stress in here the importance of reading comprehension. So if you haven't read the problem very carefully, then really everything else is no longer going to work quite so well for you. So once I'm already done summarizing in this particular concept map form the information that was given to me, a complex amount of information, I now have to find, according to this problem, the percent of copper and the percent of nickel in my mixture or in my sample. If you've read the problem, you will see that there is no equation that was given to us. So what we have to do here is that for each and every element that was mentioned, the copper, the magnesium, and the nickel, we should be able to write our equations for those when they react with the EDTA. So that's what I have right here. We take note that both the copper and the nickel react with the EDTA in a 1:1 molar ratio. That will be important later on. So once again, we try to take advantage of our data in here. We want to be able to start off in the data with that particular set in which only one I is present. We don't want the two of them at once. In this case, we only want that data wherein only copper is going to come into play. And nickel is not yet that important to us. So we have to use not this one, since this is for both cations, but rather we use this pair of information instead, since this one only pertains to the copper only. So multiplying the volume and the concentration gives us the number of moles of magnesium that we were able to use up. And looking at the equation over here, we take note that the magnesium could be related to the number of moles of EDTA. Again, remember, never lose sight of what we're after. We're always after the copper and nickel. We're not interested in the magnesium at all. Therefore, the magnesium, we have to tie it in to our copper and nickel somehow. And how do we tie it in? We tie it in by finding the amount of EDTA that is in there. So looking in this equation over here, we can now see that, oops, let me just adjust. For every 1 millimole of magnesium, 1 millimole of EDTA will react as well. And as noted in our problem, this EDTA was released in the first place from the copper. So this EDTA that I've now computed over here, I can now relate it to the mass, or rather the millimoles of copper that I have. So multiplying it now, gives me this particular stoichiometric factor. Now plugging it into my calculator, I got 1.65 millimoles of copper that is present in the 25 ml of alcohol. So moving on to the next page. So we've already treated that data wherein there's only one analyte present. The last thing that we deal with is when both analytes are present altogether. In this case, they were both present when I used up 45.81 ml of the EDTA. Now if I look back at the equations that I wrote, I took note that both the copper and the nickel react with the EDTA in a 1:1 ratio. So the number of moles of EDTA that I have in here when I titrated both copper and nickel together is related in turn to how much of copper and nickel are present in there. So there should be, from my calculator, 2.42 millimoles of cations present in my alcohol. So that's 2.42 all over 25. And so, since I've already computed the number of moles of copper only, what I want to do now is get this one when they are together and subtract it with the amount of the copper only. So what I'm able to get right now is the number of moles of nickel that is present in my sample. Now with that, since, if you recall, from the problem, there is originally a total of 100 ml of our sample, we can now compute easily the mass of copper. So this one we got originally at the previous page. So that's 1.65 millimoles for every 25 ml of alico times the total volume multiplied now by the molar mass of the copper. So by plugging it into my calculator, I'm able to find the mass of copper that's present in my sample. That's 420.39 milligrams. And since we are after the percent composition of our sample, we now plug it in. The mass of the analyte divided by the mass of the sample times 100% gives us the percent of copper. And it turns out the value is 70.02%. Now using this information right over here for nickel, I can do a similar computation to find the mass of nickel. Now once I find the mass of nickel, I plug it in here to the percent composition equation. So that mass divided by the total mass of the sample times 100% will give me an answer of 30%. Do this one for the copper and for the nickel as well. I just took a shortcut so that this video will not be too long, but in your solutions you have to show the computation for the mass of nickel and the percent of nickel as well. It's only coincidence that we have 70% of copper and 30% of nickel in here. If you recall from our example number 2, if you total the percentages that we have, it's not going to total 100%. So this one and this one giving us 100% is just pure coincidence.